I'm Vic Nelson from Auburn University. Just to give you, put my time there in perspective, the first microprocessor class I taught at Auburn, we had a rack with 4 single-board Intel 8080 computers. The students had to go to the building next door to punch their assembly language programs on cards, feed them into the card reader of that machine. It would produce their object code on a paper tape, which they then carried back to our building up to the 3rd floor, waited to their turn on a teletype, where they could then run the object code into the board and find out they made mistakes, back to the card punch in the other building. So I keep telling them if they promise not to whine about the computers, we won't talk about what we had to do back in those days. But obviously the tools have come a long way. And I think that's the purpose of the lab in a box and some of those small low-cost boards they've been developing, is to try to improve that experience, to let them focus on the things we want them to learn. Although the students were in great shape going back and forth between buildings and all that back then. So the lab in a box will have this type of user interface to it, in which you will have a number of things. Now, there's an example later in the workshop that I'll show you of the actual lab in a box. For the workshop, this is a stripped-down version of it. So what we'll do is by the way, you have this material on your memory stick. So there's an EXE file that's compressed. So if you uncompress that, it's got all this material in it, including the solutions for the lab and all that. So we'll need the solutions when it comes lab time. All right, so let me give you a little bit of an overview, first of all, of the board and the Cortex processor that's on it, and then we'll get into the lab. What we're going to do is an infrared proximity sensor experiment in lab, just to give you an idea of the types of labs that we might do with this board. So let me pull up our introduction, which is not that one. And again, the focus is on embedded system design, although we can use it across a number of courses. So as you see here, again, the idea is for this workshop to get a little hands-on experience. Of course, that's what we want for the students as well. They obviously would get their attention if they're doing something as part of the course, rather than listening to me carry on in the front of the room. Again, the material has been developed based on experience, and indeed, I've been using ARMs now in at least the senior level course for about 7 or 8 years. Through several generations of boards. It's easy to adopt for the course, easy to develop, teach the concepts we want. And again, the lab in a box will have a number of course modules that you can at least refer to get ideas, perhaps adapt your own course then to those. So as far as curriculum, again, this can be used for introductory courses. We can use it for more advanced classes. I've been using it for the advanced embedded system design class, covering some of these topics. But this summer, for the first time, I'm doing the sophomore introductory computer organization class with this. In fact, I actually, at the first day of the semester, asked the students, so we can continue with the course the way it has been taught in the past, or you can buy one of these boards and we can switch to the ARM, and they voted unanimously to make the switch. So they bought boards of the Discovery that you have now in front of you. And halfway through it, things are going well. At least I'll find out when I get back. They're taking their quiz today. First quiz. So let's talk about introduction to embedded systems in general, and then specifically this board and how that fits into things. So of course, in embedded systems, we're interested in providing some sort of probably control type of thing. Obviously we want low-cost types of things. We want low-cost components. We want things where they can ultimately can be manufactured at low cost, operated at low cost, maintained at low cost. Of course, we don't need as many features as some of the high-end systems, but we need enough features. Obviously, the thing that fits my application are the features that I need. So we need enough variety of those, and things that are fairly dependent. Of course, we make the decision, do I use a microprocessor and build my own system around that, or do we use a microcontroller? And of course, the Cortex M family has been optimized for microcontroller types of applications. Which we have on the board. So of course that includes CPU. In the case of the part in front of you, it's a Cortex M4 F CPU, so it has the Cortex M4 plus floating point. And then of course a wide variety of peripheral functions. So in addition to the CPU that you see in the center, then there are connectivity things, including USB, network interfaces, simple things like SPI, I2C, obviously onboard memory for your applications, and the memory is pretty generous. on most of the parts now. Of course, there are analog inputs and outputs on most of the boards, so this has both A to D and D to A conversion, as well as some other timers and other system types of blocks. Of course, one of the things we try to talk about is trying to do things concurrently if at all possible. So have some of these peripheral modules, such as maybe an A to D converter, operating concurrent with the CPU, which is doing other tasks. And then be able to, so I've got the things like a hardware timer, an A to D converter operating concurrent with the CPU to try to maximize, rather than having the CPU execute do nothing loops to produce delays. So I've got software over there which is setting up a timer. Periodically we get timer ticks that trigger a piece of software that might start an A to D converter, take a few samples, return to the main program. So we try to teach this type of thing. In reality, I would probably take that software bar and I would probably show that as being suspended while we do the software for the interrupts and the A to D. But nonetheless, we show them this concurrent operation of hardware working with software and taking advantage of those functions. Of course, obviously, an embedded system will have more constraints than you might in a desktop type of environment, which is what we used to teach a long time ago, at least at our place. So obviously, you're trying to minimize cost. There are performance, throughput requirements, latency requirements, size and weight limits, power consumption. So all that will impact how we do the design. So again, many of these things lead us toward a particular type of microcontroller that we might decide. Also leads us toward a particular programming language. And again, the tools that we have here support assembly language, C and C++ as our main development tools, which are primary things in embedded systems. And then, of course, we'd like to maybe bring in an operating system. And again, the tools do provide a nice real-time executive that you could use if you'd like to start with that as opposed to one of the other commercial operating systems. All right, so let's talk about the processor we're going to use. ARM obviously makes a wide range of processors. The Cortex A family, those are the high-end type things that you'll see in smartphones and tablets and what have you. Very performance intensive. They have a real-time version, the Cortex R family. We're going to deal with the Cortex M family, which are the cores that were designed for small, low-cost microcontrollers. And there's a wide range of those. So they go from the very simple M0 up through the M4. And as you look at, if you look at the instruction set, the M0 instruction set is a subset of the M1, subset of all the way up through the M4. And for instance, for the sophomore class, I'm just teaching, even though we have an M4, I'm just teaching the simple instructions that would be in the M0 to teach the computer organization concepts. And I tell them you can certainly take advantage of the more advanced instructions that are in the M4 if that's of interest. Of course, the M4 processor, everything includes the M4 and a memory interface, and then you see in here a number of optional modules. So when you get Cortex M4 parts from various manufacturers, the floating point unit is optional. That can include some of the debug things are optional that may or may not be included. The version we have does have these on board. And then most of the microcontrollers include the debugging interfaces. So the boards that we used prior to this one, we had to have a separate debug module to connect between the debug tools and the board. And the ones we had actually connected to parallel ports on computers, which are harder to find these days, if not impossible. So now they've built the debug interface directly into the chip. So basically you just connect a USB cable and you're ready to go. The instruction set in the Cortex, which I found out in the M4, is a Thumb 2 version of the instruction set. So, of course, the Thumb was developed in 1995 as a way of producing low-cost systems with small footprints in memory. So basically what you do is you take the basic ARM instructions and you encode them in 16 bits rather than the usual 32-bit instructions. Of course, we teach reduced instruction set computers where every instruction has the same size, 32 bits, and the same types of formats, but then they decided, for low-cost type things, it'd be nice if we could just take a subset of the instructions and get it down to a 16-bit code. Now, inside the CPU, it still expands back to the 32-bit instruction and is executed, but at least it minimizes our footprint in code memory, so it takes up less space. And then, of course, they saw the limits of that and said, well, the higher performance people, we probably ought to throw some more advanced things, so the Thumb 2 came along, and that does add some 32 instructions back into the 16-bit instruction set. So if you look in the debugger, for instance, I'm teaching the assembly language class this summer, and if you look in the debugger, then look at the code memory, you will indeed see the disassembly window. You'll see 16-bit instructions, and suddenly you'll see some 32-bit ones, and so forth. So it basically fits those in where necessary to provide performance. So as I mentioned, it's the thumb instruction set. It does execute only in thumb state, so you cannot switch to an ARM mode like you can in the, for instance, the Cortex A processors. So there you can switch back and forth between thumb and ARM mode. If you want to save memory for a while, you can switch to the thumb mode. If you want to go back to the full instruction set, you can switch to ARM mode. And generally that's done by using the least significant bit of the program counter to indicate which operating mode you want. So in the case of the Cortex M, however, which just has a thumb mode, there's a bit in the status register which indicates which mode it's in. That's hardwired to 1. So obviously we can't jump into ARM mode. It's a 32-bit address space. So if you want to assign projects that use 4 gigabytes of memory, you can do that in class. Of course, the instructions 16 bits are aligned on half words. So let's take a look at the platform that we're working with. So the Discovery platform uses ST's 407 microcontroller. So that includes both DSP support and floating point unit, in addition to the regular integer Cortex M instruction set. Can run up to 168 megahertz max in the core part of the CPU. Some intricate clock setup in there so they can generate those higher clock rates if you want the performance. It's got up to a megabyte of flash and plenty of RAM to do various applications, and then a wide range of peripheral functions. By peripheral functions meaning timers, A to D, D to A converters, communication interfaces, and the like. So a very rich set of things that you could use. The board, which probably by the time they put in shipping and handling, may cost the students $20. So I think they sell in markets for about $15. And again, in addition to the on-chip peripherals, this board has a MEMS accelerometer, MEMS microphone, an audio codec. So they can do a wide, so probably, for instance, in the advanced classes, we can take advantage of those. So I have students in the advanced class do a music generator using the audio codec and the microphone, and then they build the equivalent of a Wii controller with the accelerometer on board. So it's a good range of projects you could do with this type of board. And they do come, by the way, you can get a zip file from ST which has a wide set of examples, as well as the software now, as well as their zip file will include all the drivers for the peripheral functions. So if your goal is to use the peripherals as basic building blocks and not design the drivers for those, you can start off with drivers and then build your application on top of them. So as far as the software development tools, again, we're going to use the microcontroller development kit from ARM. In the case of my sophomore class, for instance, it does include simulators of each of the microcontrollers that it supports. So early in the course, they're just using the simulator just to test some assembly language on the CPU. And then we'll be getting outside the CPU into some board level projects the second half of the semester. Of course, in the embedded system class, obviously, we'll interface outside. So again, the tools will support all the Cortex processors. Provides the basics peripheral simulation and core simulation, so they will simulate things like the programmable timers and all that, some good debug stuff. It will program the flash memory on the board for you. And again, then the kit includes the standard integrated development environment, so editor, debugger, all in one module, fairly straightforward to use, and similar to what you might see from other manufacturers. So we switched from a different manufacturer to this set of tools this semester pretty seamlessly. For the courses, it does include the Cortex microcomputer software interface system standard support, as well as the real-time executive for real-time operating system support that comes with that. So in the advanced class, for instance, we spend the last third of it talking about how to design with a real-time operating system. And indeed, that provides enough features for me to do that without having to bring in yet another real-time operating system to include in my projects. So good support for that. All the debug hardware is available. Nice software interface from the debugger into the board so you can do real-time debugging, get feedback back from the board, and we'll take advantage of that here this afternoon. So in our lab, what we'll do is I'll introduce the project here in a moment. The goal is for me to talk less and for you to work. So we'll do that for a while, and then we'll probably take about 15 minutes at the end of the session then to just do a final wrap-up and a better introduction to the lab in a box type setup. So we're going to, if you don't already have it installed, we're going to install the MDK ARM software. On your memory stick is the main software installation file, And as I'll show you in a moment, it includes a package of stuff to support this microcontroller. And we'll show that. Once we get in there, in the integrated development environment, there's the setup for producing your source files, compiling, getting rid of errors. And then we'll go into the debugger. So there's a debug button, which switch you. And then as part of going into the debugger, if we have it set up that way, it'll program the flash memory on the board for you. If you prefer to use the simulator, it will load your software into the simulator memory. And then in the debugger, then we have things for resetting, running, single stepping, setting breakpoints, most of the usual things. Okay, so with that in mind, let's talk about the lab that we're going to do. By the way, if you have any questions anytime, please just flag me down there because I tend to go zipping through. Yeah.
Sure. So for teaching purposes, we do offer the full MDK Pro, which is complete. You know, it's not limited in terms of size of the code and also the libraries that are involved. But the size limited, the code limited version is free for everybody to download. So you don't need to do. You go to the Kyle website and you download it, and there is no qualification or anything like that. But for teaching purposes, you could get a donation of the full professional suite. Within classes, within universities, they do. So it's not a license, individual license, but you could have 100 floating license. So if they have access to VPN, for example, they could use it from home. So university at ARM.com, the website as well, you could request a donation just for software if you want just software, or you could request a donation for the full lab in a box, which contains the software component of it. So if it is for teaching purposes, the full professional suite is available. We typically donate 100 floating license.
Now, for the sophomore class this summer, I said, you know what, I told them, if you need more than 32K, you need to bring your program to me, let me look at it, because you probably missed something in there someplace. So that will handle student projects for those types of classes, but for the senior class, indeed, I contacted them and got them to donate licenses for the students to use.
It shouldn't be a problem. If it's for teaching purposes, it's nearly automatic.
All right, so let's talk about, we're going to do an infrared proximity sensor lab here. So the learning objectives, of course, as soon as you put functions on a board, we want more functions that are not on the board. So we're going to talk about interfacing to a breadboard for some simple components. We're going to interface that to that. We're going to use an infrared light emitting diode and then a phototransistor to sense the signal. We're going to see how much light is reflected back and be able to measure that. So we're going to convert that to an analog voltage, run that through an analog to digital converter, and then we'll take the value and we'll basically use the intensity to try to light some LEDs, different sets of LEDs on the board. So that's the thing in a nutshell. So on the board, you're going to have the IR LED. That'll be broadcasting, and then sitting next to that will be the phototransistor. So what we do, of course, if we don't otherwise reflect the signal back, obviously I would expect the phototransistor to just sense ambient light in the system. So we're going to go ahead and then set that up. We'll actually measure the ambient light, and then we'll compare what's reflected back. And then we'll try to, as part of your experiment, is to find a way to reflect light back to the phototransistor and then measure the difference in sensed light there versus the ambient condition. So again, we'll have those two components set up. And again, we'll use the differential measurement. So again, we'll do it with the ambient light, and then we'll do it with the reflected light. And we'll alternate measuring those two and then look at the difference between them. Now, of course, the phototransistor does have some response time issues, so I need to make sure that I allow the phototransistor time to settle to its new value once I change the light conditions. So what we're going to do is we're going to drive the IR LED with a little pulse width modulated waveform there. So we'll turn it on for a brief period of time, then turn it off. And then again, once it's been on a significant amount of time, we'll measure light. And then once it's been off for a while, we'll measure ambient light. And then we'll compare those two values to find out how much is being reflected back. All right, there's the circuit that we're going to implement. So as you see over here, there's a digital output which is the pulse width modulated waveform that I mentioned. So that's going to go to the negative end of a diode there, and it's going to turn that IR LED on and off periodically. Okay, and then while it's on, obviously it's going to emit light, which will be picked up by the phototransistor. The output of the phototransistor will go to an analog input on the board. So we basically have two connections to the board. So we'll drive the LED with one, and we'll measure the analog output of that phototransistor with the second connection. And then, again, this will be active low, so a 0 will turn the LED on, a 1 will turn it off. Okay, and then we'll measure the difference between the two, and we may make some adjustments. So these are the 4 components. So you got a package of components when you came in. So obviously you've got the board and then a USB cable. By the way, the USB cable connection is the one opposite from the side with the microphone connection. So it's the mini, USB mini connection. The 4 components, we've got a couple of resistors we need for the circuit back here. So one to limit the current through the resistor, one to bias the phototransistor. So we'll have those 2 resistors. And then you've got 4 test leads. So we'll be able to connect to the board with 4 leads. So we can actually got a picture of the setup here. When you get done, it's going to look like this. Okay, so you'll be connecting onto your breadboard. We'll connect to these pins. So these pins are all on one side of the board, so to make it easier to line up the board with your breadboard. And notice you have the IR LED. So the long lead is the negative terminal. So you'll need to be aware of that as you're plugging and connecting your circuit. The long lead of the phototransistor is its negative, the short lead, excuse me, is its negative terminal. So you need to be aware of that as you plug that into the breadboard. So basically we're going to wire that circuit on the breadboard. And again, it will look something like this when we get done, connect that, and then of course now we're ready to start our project. So basically what we're going to do is we're going to make sure that, of course we're going to have a project we'll have to set up, and we'll talk about that in a moment here. Make sure we have light that we're seeing, figure out how do we know the IR LED is on. Of course it's infrared, so you may or may not be able to see blinking like you would with a regular LED. So you might think about things like cell phone camera. If you have a camera, cell phone with you, the camera can often pick up IR type stuff. So you can use that to verify that your LED is blinking on and off. The software that we're going to provide, it's actually in there. So in the workshop, if you click on the code, that's going to download a zip file to your computer, and then you can unzip that. That's got the software solution there. So we can design a project, and in the software, we basically are trying to, again, for the students, illustrate modular design. So we don't want to, many of the students want to just sit down and write lines of C code for a project. We have to convince them back up and take a look at the system and what are the pieces of this design. So in our case, we have the A to D converter, and we would probably provide and then have them design separate functions to initialize the A to D and then actually get A to D values. We've got software to control the IR LED. So that'll be some initialization, so the parallel port pin to which the LED is connected will have to be initialized, and then we'll have functions to turn the LED on and off. So again, we want to get in the habit of students developing these and testing those independently. And as I tell them, if it doesn't work when you're testing independently, it's definitely not going to work when you put it in the middle of this large project. So we want to have some nice individual functions we can test. There are 4 color LEDs on the board. So we'll use those to indicate the intensity of the light that's being reflected back. So as the light gets more intense, you'll see the LEDs change colors. So we'll have an initialization, and again, the initialization function will set up the parallel ports to which those LEDs are connected to make sure we can drive those, and then something to actually turn one of the LEDs on based on the voltage differential between the ambient light and the reflected signal. Okay, so we're going to do that. There'll be some timing. In this case, we're just going to use a software delay loop for the timing. Of course, in other projects, you may want them to get used to using the programmable timers to provide more accurate timing of those. And then the application software then, so what we'll do is we'll call a function that basically says take X number of readings of the A to D while it's in the off state, and then we'll average those, and then save that number, call it again with the LED on. Take an average of a certain number of samples, compare the off versus the on, so the ambient light versus the reflected light, and then use that to decide which of the colored LEDs to turn on. So in a nutshell, that's what the lab. So of course we tell them the basic main program should be fairly minimal in size. So I'd like to emphasize that in your main program, it should primarily be calling functions for the individual pieces that we have designed, rather than just having this big long page of code in there. So we'll call the initialization functions, and then the application is, again, turn the LED off, wait for everything to stabilize for a little bit, and then make some measurements. Then turn the LED on, wait for a little while, make some measurements, and then take the value with the LED off versus the LED on, take the difference between those, which is our reflected light that we've sensed, and then call our function which turns on one of the colored LEDs, and just repeat. So that's our application. So as far as program setup, of course, we're going to download that to the board and debug. One of the questions is, how do I know if this thing's doing what it's supposed to be doing other than the colored LEDs turning on? And the nice thing about the debugger is you can examine most variables and other pieces of information in the system. So it uses the single wire debug interface to the microcontroller to both download stuff to it, but as well as get stuff back from it during debug. So we can set up a watch window and display the variables. So the voltage reading went on, the voltage reading went off, and then the differential between those. Another nice tool I found, by the way, they also have an oscilloscope in there. So I could add these to that oscilloscope and I could watch those values change over time as well. So they just take a digital value and then display that level. So that's a valuable tool during debugging. So this is what we'll do in the lab, and before we get to this then, let me talk about the software setup. So if we go back to the lab setup, and again, you've got the whole, if you unzip the executable, it's on your flash drive, it unpacks this whole lab, and keeps wanting to switch modes on my computer. Okay, so the presentation I just covered is this. So the lab exercise is what I just went through. And then this is the code solution here. So if you click on that, that's a zip file. So just download that and unzip it, and that will be provide the solutions for this code. So what we'll do is, rather than, we don't have time to write the programs, so we've provided the source code in one file there. So you can copy that into your project. But we do need to create a project. So we need this getting started document that's listed up here with the introduction. So in the getting started document, so how many of you have the software already installed? How many have yet to install it? Okay, so there's a copy of the... I'm going to run get my laptop. Okay, but there's a copy of the MDK ARM on the system, and also we need a package of support tools for this microcontroller. So starting with version 5 of their software, they now have a base system that's installed, which has the editors, debugger, compilers, that type of thing. And then there's a series of packs. So the old versions, when you installed it, you got all the stuff installed for every microcontroller they supported in there. So now what you do is you select certain packs to be installed along with the software. And the one we want is for the STM32F4 series. So basically that will provide all the stuff. And this includes things like startup code, peripheral drivers, that type of thing for that microcontroller. Okay, so if you don't already, how many, has everybody installed that pack, or how many do not have that pack? What? I'm glad you asked that question. If you scroll down, I've got instructions. So if you install it during the installation process, it will pull this window up and say, which packs would you like to install? And if you have an internet connection, it will go out to the appropriate website, ARM website, and bring those down and install them. If you had not installed it previously, then I provided the pack on this, the third file on your USB stick. So that's the pack for the STM4X series. So what you would do is you would open the tool, and then there's a pack installer under the project manage. So there's a link there, project manage pack installer, and it'll bring up a window, and you would select that file and say install the pack that's in that file. Okay, and then that'll be needed. The other thing you will need is to interface to the board, you do need an ST-Link USB driver. So that's the driver for the USB connection to the board. ST-Link is the debug interface that we will be using. Okay, so if you have not already done that, we'll need to install that. So you'll need that to communicate with the board when it comes time to download and debug. Okay, and then here's the instructions for installing that. They include the drivers for that as part of the MDK ARM installation. So you can navigate, as I've indicated here, to where the drivers are provided for ST-Link, and you can install that. So basically, if you, when you plug the board in, it'll say, I need to go find a driver. Would you like to tell me where it is? And you can tell it that it's located there. Okay. And then now, next thing we'll do then is we need to create a project. So for every one of these, then we'll create a project for Microvision, as they call it. So in the menu, there's a new project. When that opens up, it'll ask you to select a device. So in our case, it's the STM32F407VG microcontroller, which is the part that's on the board. Then it will bring up a window and ask you if you want to add some components to your project, things like peripheral functions and what have you. So we're going to install the CMSIS core, so that's the Cortex Microcomputer Software Interface Standard. We're going to include the core support for it, and we're also going to include the startup code. Of course, the startup code is executed before it gets to the main function of your C program. So we'll do that, and it'll automatically plug those pieces then into your project, and then you just need to add your source file. So I've got instructions here then, so we would use this, then we would add source files. Again, the source file would be the main file that's in the code solution zip file that I mentioned with the lab. So if you unzip that file, you can find the main file in there. You could either, in this thing, say add that file, or you could copy and paste the code and create a new file, if you wish. So as students create this, then you can give them files to work with, or they can, you can have them and link those into the project, or you can have them create their own. Obviously, for many of our courses, they would be creating their own. Okay, for this lab, we'll probably want to go ahead and use the one that we provided just to get you up and going. For extra credit, though, if you want to write your own, we will give you extra credit for the workshop, and I'll make sure he gives you a prize. All right, so this goes through the process. So we will build the program, compile it, get rid of compiler errors. Hopefully, if you use our example, there are no compiler errors. And then go into debug. So when you debug, then we will have to do some setup, and I have windows for each of those down here. So as you create a new project, again, you'll create a project name for it and put it in a directory. Okay, then you will select a microcontroller. And what it does, it gives you the menu of microcontrollers supported by whatever packs you have installed. So if you don't see this set of microcontrollers, you probably don't have that pack installed in there. So we would select that microcontroller. This is the window then where you would select the CMSIS core functions to be included in your project, and you'll also select the startup code to be included in your project. So for instance, when I'm doing the assembly language class this summer, we don't need these things. So right now, they're just doing some simple assembly language programs. We skip this. Question? Well, there's a distinguished professor from the University of Texas, Jonathan Valvano, whose book I'm using this summer. And I'm sure he would be glad to give you more information about it. And you know, his book covers a T. So he's from Texas, so he has to cover a TI thing. So it's state law. Okay, but okay. So anyway, so obviously he would have a different board, but basically the book covers. We've used the assembly language coverage thus far, some of the C programming type stuff. Obviously that's common to all the Cortex microcontrollers. I'm going to have to write some of my own stuff to talk about the peripheral functions. But the concepts are still the same as what he covers in his book there. So that's a nice little book to get started with. Okay? And you can give me my finder's fee after the workshop. Okay, so once we get going then, this is the integrated development window. So you've got a project pane on the left which lists the programs in your project. Of course, it's going to include the CMSIS and the startup code. We added, then up there you'll see source group number 1. So that's where you'll add your project code. And again, if you use the zip file we provided, then there's a main program in the zip file, and I would just include that. Or alternatively, you could create a new file and you can copy and paste the code into that. Then the compile button's on the upper left there on the menu bar, so you can build the project. Now, before we execute it, we'll have to open up options for the target. So there's a tab right above the editor window there, and next to where it says Target 1, Group 1, and then there's a little tab there. You click up, and that's options for the target. So among other things, we'll go to the debug tab, and we will tell it not to use the simulator. There's a button on the left if you want to just use the simulator. But on the right, we'll click a button. We're going to use a specific debug interface. And in our case, it's the ST-Link debugger. So we will select that. There's about 8 or 10 different debuggers that they support on there. So we're going to use the ST-Link debugger. And next to that, there's a button called Settings. So we'll click on that. And where you see it highlighted in the middle, in the blue there in the middle of the screen, we're going to select the single wire debug port. So they've got 2 debug ports. There's a JTAG port and single wire debug. Make sure we select single wire debug. And then there's another tab called Flash Download. And on that, we want to make sure that it programs the flash when we go into the debugger. Now, if you just want to debug something that's already in memory, then you would uncheck those. So when it goes into the debugger, it would use what you already have on the board. But in our case, of course, we want to program the flash memory with our application code. So we'll make sure those are checked. And there's a button right below that big window saying Add. You click on that, it'll bring up a list of flash programming algorithms that it can use. And we want the one specifically for this microcontroller. I've got a Mac user in my class, and he has to come use the lab that I've got available. So most of the students are running on their own PCs, but he's coming in and using the lab. I don't know, do you want to comment on Mac?
Yeah, well, I can't say when, but there is a plan to basically make it available on other operating systems. But I can't give you the exact date because we don't know. But we are aware of this problem, and hopefully we'll sort it soon.
There's always one in the class, too. And of course, holy wars have been fought between the Mac and the PC users, so we won't get into that here. But nonetheless, this is PC-based. All right, so that gives you the project setup. So, and then, of course, once you go into the debugger, then Windows, you have all the registers available on the left. So that's been valuable, for instance, in the assembly language class, to have them watch the CPU do what it does by watching registers change as they execute instructions. The top window there with the big yellow stripe in it is a disassembly window. So again, it shows you the disassembled code as it's being executed. Your source code is in the middle window. Down at the bottom, you can have a block showing memory locations. We have a watch window here where you can specifically say watch certain variables in the program, and then a place to type in commands. So that's the basic interface, and there's a nice getting started guide on the ST website, so there's a link to that down there that you might use when you get back. All right, so without further ado then, what we'll need to do is go ahead and start the project. So you've got a couple of things to do. You've got to build a circuit, you've got to connect it to your board, create a new project, bring the project code in, compile that, and debug. So what we'll do is let you start working. I will walk around and see how things are going. But right now, this is the hands-on part. Okay, so if you don't have a setup, please get together with someone who's got a setup and work in pairs if you want. Questions? Okay, so what we should see, let me bring up, I've got my version here. Matter of fact, let me get my setup and connect. And if anybody wants to see the working version, I got one up here. Okay, so under here, so if we go to where it says Pack Installer, so if I click on that, then up here under File, I can navigate to the file and import the pack that's on your USB stick. Hopefully that, and when I did it, I copied it to my desktop first and then installed it, so. I'll walk around and take a look. So if you have not already installed that pack, then the pack file is on the disk. And
I installed the pack right from Kyle.
And yeah, if you have web internet connection, then it downloaded directly from Kyle.
I opened up Kyle.
Mm-hmm.
We went to update or there was a button that allowed me to add pack installer.
Right.
And then in pack installer,
And that didn't work?
It worked, yeah.
Oh, okay, okay. Okay, so I'll walk around and take a look. So go ahead and get started, and we'll walk around and see what we can do about fixing problems here. So everybody go ahead and get your project created, get to this point. So in my case, the project should look like this once you open it. As I mentioned, the target options window is up here, right next to that little box. And again, you'll want to set up the debug tab there. Make sure you select that debugger, and then under settings, single wire debug, and make sure you have the right flash programming algorithm. Okay, so once that's set up, we can go ahead and build the project. Hopefully you get 0 errors at the bottom of the screen, and then I can click on the debug down here. So when I click on debug, that's going to go to a program, the flash. I've got the evaluation mode here, so it always gives you that nasty little error message, or nasty message. But, so if you get the regular license from him, obviously you wouldn't see that. Then we're in the debugger. Stuff is now programmed on the board, ready for me to start, and I can just click on start up here. And you notice I've got some watch variables down here that are changing. So one of these is the LED voltage reading when the LED is off, the voltage reading when the LED is on, and the differential between them. So as he changes light, we should see the voltage reading when we should see the differential changing there as his hand gets closer. Okay, so that's what it should look like when we get done. Okay, so let me leave that on here. Let me point out one thing. I did make one change to the program on. These 3 variables right here, the 3 variables that I'm displaying in the watch window, they were in the main program, which means that they are out of scope if you're in other functions. So what I did was I made them global variables. So I just cut those 3 from under integer main, and I moved them right above there so they'd be global variables. And that way you can always see them in the watch window. Okay, okay, let's everybody work. What time did we say the quiz was going to be?
Is there a secret to getting the board out of the
Yeah, getting the board out of the way.
This is self-installing.
I say the kind of installation different. So if you go to, should be under C drives, and then you should see an STM.
people, you know, especially when they go into their computer science, other professors, those are very levels.
Right, and tell them never to do that.
Yeah, tell them to never do that, that's the first thing to do. Right? Sometimes they get zero.
without really going through them. I hate to interrupt everybody who's working so hard out there. So what I've got in here is a summary of my 3 courses at Auburn, if anybody might be interested. So there's the sophomore level one, the junior lab that they do, where they apply all this, and the embedded system elective that they do senior year. The first one is the one I'm actually converting this summer using Professor Valvano's book. So we're doing assembly language type stuff. The junior lab, we've been using a different part. We're going to use one of the other discovery boards in that this fall, and I've been using the discovery in the other class for a while. So then these are brief outlines as well as links to the web pages for those courses if you might be interested. As far as the lab in a box, the rest of this presentation describes the lab in a box briefly. So this kind of gives you an information of what all is in it. So you'll see that for each one of the modules, as are shown here, then you have a module name. There are lecture materials, so the PowerPoint slides are there. You have homework exercises and solutions for each of those modules. There's demonstration code for some of them, and then there's lab exercises along with the code, and then finally some suggested projects. So you have these for each of the course modules. So you see some of the course modules listed here. Here are the other ones. So this is what would be in the lab in a box to go with this board. And again, he has similar ones for the other lab in a box components. Okay, and then there's some other miscellaneous information in here that you might find interesting. So with that, let me ask Colette if you'd like to make some concluding comments.
Thank you very much, Victor. Thank you very much for everybody for attending the workshop. I hope it's been useful. Karthik has just distributed feedback forms. If you can fill them, that'd be great. Let us know what you think of the presentation, what could be made to make it better. As I said, this is just the beginning of a conversation. We can't cover everything in an hour and a half. So go to our website. That's our main way of interacting with professors. Register there, send there your comments, let us know what you're teaching, what you would like from us, and we will basically start a conversation with you and hopefully fulfill your requirement. As far as this lab in a box is concerned, as I said, it's very useful for embedded, either introductory or mid-level embedded system courses. So you can adopt these. It's full of useful material, including lab solutions, lab manuals, and lab solutions. The good thing about this board is that we have developed 3 lab in a box around it. This one on embedded systems, a DSP lab in a box, which Professor Donald Ray will present tomorrow at 4 p.m. in room 126, just next door. And another one on operating system as well. That'll be ready by September. So you could use the same platform for 3 courses. We could share with you sample chapters. Just go to the website, request a donation, and we will take it from there. Thank you very much, and hope to see you soon. Thank you.
Without really going through them. I hate to interrupt everybody who's working so hard out there. So what I've got in here is a summary of my 3 courses at Aauburn, if anybody might be interested. So there's the sophomore level one, the junior lab that they do, where they apply all this, and the embedded system elective that they do senior year. The first one is the one I'm actually converting this summer using Professor Valvano's book. So we're doing assembly language type stuff. The junior lab, we've been using a different part. We're going to use one of the other discovery boards in that this fall. And I've been using the discovery in the other class for a while. So then these are brief outlines as well as links to the web pages for those courses if you might be interested. As far as the lab in a box, the rest of this presentation describes the lab in a box briefly. So this kind of gives you an information of what all is in it. So you'll see that for each one of the modules, as are shown here, then you have a module name. There are lecture materials, so the PowerPoint slides are there. You have homework exercises and solutions for each of those modules. There's demonstration code for some of them. And then there's lab exercises along with the code. And then finally some suggested projects. So you have these for each of the course modules. So you see some of the course modules listed here. Here are the other ones. So this is what would be in the lab in a box to go with this board. And again, he has similar ones for the other lab in a box components. Okay, and then there's some other miscellaneous information in here that you might find interesting. So with that, let me ask Colette if you'd like to make some concluding comments.
Thank you very much, Victor. Thank you very much for everybody for attending the workshop. I hope it's been useful. Karthik has just distributed feedback forms. If you can fill them, that'd be great. Let us know what you think of the presentation, what could be made to make it better. As I said, this is just the beginning of a conversation. We can't cover everything in an hour and a half. So go to our website. That's our main way of interacting with professors. register there, send there your comments, let us know what you're teaching, what you would like from us, and we will basically start a conversation with you and hopefully fulfill your requirement. As far as this lab in a box is concerned, as I said, it's very useful for embedded, either introductory or mid-level embedded system courses. So you can adopt these. It's full of useful material, including lab solutions, lab manuals, and lab solutions. The good thing about this board is that we have developed 3 lab in a box around it. This one on embedded systems, a DSP lab in a box, which Professor Donald Ray will present tomorrow at 4 p.m. in room 126, just next door. And another one on operating system as well. That will be ready by September. So you could use the same platform for 3 courses. We could share with you sample chapters. Just go to the website, request a donation, and we will take it from there. Thank you very much, and hope to see you soon. Thank you.